There we go, finally. Can y'all see that now, still up there? All right. I think we're there. Still trying to figure out why it does some of the stupid stuff it does. There we go. All right, so this is a super long chapter here. She covered a lot of stuff in this one. But basically, we start off with the introduction to the nervous system, and it's going to go back over the axe potential that we did the other day. Okay, so what does the nervous system do? So let's just run through it pretty quick here. So we'll try to knock it out as much as we can. Like I said, 14 at the end is extremely short. Well, this is a big one here. This controls all perceptions and experiences of your life. Everything, you know, all direct voluntary movement, consciousness, personality, learning, and memory, which we've done a lot of testing of your memory these last 3 weeks. So who you are, the essence of who we are is in the nervous system, in the brain. I think there's a soul. If there is a soul, it's in the brain. Okay, it's these combination of these neurons firing in the brain would be my guess there on that. But anyway, so it does all these super memory, all your who you are, personality, and then it controls the entire body. Okay, so it has this huge control over the endocrine system, respiratory, blood pressure, temperature, sleep, weight cycle, blood pH, and all controlling all these electrolytes and vitamins and calcium and hundreds of different homeostatic mechanisms that are maintained by the brain. Okay, now the brain is broken down into 2 big groups, the CNS and the PNS. The CNS is the central nervous system, and that is the brain and the spinal cord. The peripheral nervous system are all of the nerves coming off the brain and the spinal cord. Okay, we're going to find out that there are 12 cranial nerves that we were talking about in lab on Thursday when we looked at those brains. They come off the brain and go out to the body, and of course, they go back to the head and stuff. And then there are 31 pairs of spinal nerves that come off the spinal cord, coming out the vertebral in between the vertebrae, going all the way down the back. Then you've got 2 or 3 down in the sacrum that are not considered those, but spinal cord ends, and then nerves go down through the sacrum. The brain contains billions of neurons that connect together, and that sequence of connecting is how we do long-term memory and personality, et cetera, et cetera. The spinal cord contains millions of neurons that we saw in that butterfly, right, in the spinal cord slide, that control reflexes and control movements of the body, et cetera, et cetera. So spinal cord also super big, and it allows the brain control center to communicate with the body. I think I told y'all that somebody said that the number of neurons in the brain probably equals the number of trees in the South American rainforest, and the number of synapses between those neurons represents all the leaves on the trees in the South American rainforest. So tremendous amount of stuff going on here, but no one's been able to draw on the board with the pencil or chalk grandma's biscuits, memory of grandmother's biscuits yet. So still not completely understanding how this thing works. Okay. The PNS, there we go, has 12 cranial nerves, and we looked at those. We'll go through those again. We did look at them in lab. Okay, and then the spinal nerves have 31 pairs coming out of them. Here we go. Here's Inviso Naked Boy. Then you can see on the left, the CNS is the brain and spinal cord. On the right is the 12 cranial nerves, and then the 31 spinal nerves, plus the branches here going down, right down here, going this way, down, going down the back, the tailbone, the sacrum. Okay, now, we can also break the nervous system down into the type of nerves that they have. Okay, so we would have nerves that are sensory, that detect information and carry them to from the PNS to the CNS. Okay, so obviously we're going to have lots of sensory neurons. Okay, these are called afferent, are those, look at that, afferent division. The PNS gather information about the internal and external environment and carry that to the brain, spinal cord or brain. Then there can be the somatic sensory division that carries signals from the skeletal muscle, the bones, the joints, and the skin, and the organs of vision, hearing, taste, smell, balance. All those are going to come in too. Then we have sensory receptors in the visceral that go to all the internal organs. Visceral refers to like gut stuff, heart, lungs, stomach, small, large intestine, kidneys, bladder, et cetera, et cetera. So sensory neurons are going to bring things in. Then we have in the brain and spinal cord, specifically those motor neurons we saw in the spinal cord and up in the brain, we have what are called integrated function. And these neurons are going to analyze the input from the PNS, all that sensory information, and then they're going to make a subconscious decision, right, to how to respond to that stimulation. So these integrated neurons analyze, interpret the information, and then determine the appropriate response. Okay, now this is where it gets kind of crazy. So if you step on your toe, if you did back over my toes with your car, what would be my response? This morning, I would probably decide to say some 4-letter words, right? But you can train yourself not to do that, right? You can train yourself on what you choose to say when you hurt yourself, or you can modify your responses. We'll talk about that later. Look at this. 99% of integrated sensory information is subconscious and is disregarded as unimportant. So your brain is filtering out 99% of the information coming to it as not important. And that's kind of a big deal to me. So we got sensory, bringing information in, brain, cerebrum, spinal cord, medulla oblongata, sitting here going, okay, how do we respond to that? And then the appropriate response. And so in general, here's another weird word. When you see the word afferent, that is referring to things coming into the brain and spinal cord, that's sensory coming in. Integrative is decision-making. And then motor functions are those going out that are sometimes are called efferent with the letter E. So they carry that information back out to the body in the form of motor neurons that can tell skeletal muscles to contract, or others that can make the organs in the body to respond to the appropriate response. So in essence, what you've got here is, and I'm going to show you a picture of here in just a second. You have, this is how our brain is set up. We have sensory input, we have integration in the brain and spinal cord, and then we have motor function coming out to respond to that. So I see a ball, I want to kick it, I do all the, send all the action potentials out that are needed to make the body go and kick that ball, then I execute it. So sensory input 1, integration, what do I do about it, what am I going to do, and then 3 is fulfillment of that. Okay, pretty cool. Now, that would be really easy if that was all there was to it. But here's another picture of it. So we have sensory, we have the CNS and the PNS. And look on the left. Here's sensory information coming in, but information going out of the nervous system is broken up into 2 groups. I believe that's what this picture right here is referring to too. So the motor neurons, those neurons coming out of the brain and spinal cord, going back out of the body, are broken up into 2 groups. Okay? And that's talking about this autonomic. Okay, you have the motor neurons, which are totally somatic. Those are conscious control. They're going to go out and you consciously make something move. And then we have a group of nerves called the autonomic nervous system that you do not have conscious control over. Okay? So the autonomic nervous system are going to come out. Let's go back to this picture. And here it is, again, laid out. Sensory, integrated function, motor function. Somatic nerves go to skeletal muscles, conscious control. Our whole legal system is based on that. But this autonomic nervous system is very bizarre. It has 2 sets of nerves going out to all the internal organs, okay, and to all your blood vessels. Okay, so think about it. Heart, all the digestion, all the internal organs have 2 sets of nerves. These autonomic nerves, 2 sets of them come out to the organs. Now, normally I would actually stop here and jump over to another chapter, and I may do that anyway, just to lay out the groundwork of this, because to me this is very weird the way they present it. This autonomic nervous system actually comes down, and those 2 nerves of it, they're 2 sets of nerves that are called the sympathetic and parasympathetic nervous system. Now, y'all probably heard of this before. So in other words, all these organs, the heart, for example, has both a parasympathetic and a sympathetic nerve going to the heart. And once again, I am not criticizing God. I would no way ever try to imagine why he or she did what he did or it did. But one of the weird things that God did here is, I would have thought one of them would be what? Because I'm thinking car here, right? Driving. You have an accelerator and you have a brake, right? One would think we would not have that. God did not do that. God has 2 sets of nerves in this autonomic nervous system. Both of them are sending action potentials out. And one of them is not a brake. And this is how it breaks down. I'm going to go, I may just go ahead, and I don't really want to jump over there. I'm just going to verbally tell y'all, then we'll look at it as we go, because I have enough problems with this electronics. But once again, let me break them down. I would almost take a pen here. Oops, I'm not even going to do it. I'm not going to do it. And I'd break this one down into sympathetic and parasympathetic. I'll just walk you through it. The parasympathetic nerves are the ones, mainly the vagus nerve that we saw in lab. That vagus nerve, one of the 12 cranial nerves, it goes down to all the internal organs, and it is going to speed up all the organs that are needed to maintain housekeeping, like digestion, respiratory, all the digestion speeds it up. Urinary function speeds it up. All the juices of the digestive tract speeds it up. Liver fires it up. But it stops the organs that are needed to survive for the next 5 minutes, or it slows them down. Then the other one is the sympathetic nerve, okay, and it's usually one of the spinal nerves, and they go out to all these organs and they fire up all the organs that you need to be alive for the next 5 minutes. And y'all heard of this before. It's called the fight or flight. Y'all heard that before, right? Fight or flight. So those sympathetic nerves are going to speed up heart rate, breathing rate, intense energy to muscles. They're going to cut off digestion, all the housekeeping stuff. So those sympathetic nerves stop digestion, stop urinary function, stop, packing poo-poo in the rectum or whatever, all this kind of crazy stuff. It stops all that housekeeping, but fires up things that we need to live for the next 2 minutes, including the hormone adrenaline, which gives us this burst of like energy or whatever. So this autonomic nervous system has two accelerators. One accelerates fight or flight while slowing down all the housekeeping, and then the parasympathetic nerve that speeds up housekeeping and cuts off the sympathetic or the fight or flight one. Okay. Now I'll come back to that several times, but she doesn't want to go into it here. But that's it. That is your breakdown of the nervous system. Once again, sensory, integrative, motor functions broken into two groups: somatic, conscious control; autonomic, not conscious control. Autonomic is broken down into sympathetic, parasympathetic nervous system, and that is actually chapter 13 that we'll fly through very quickly, and we'll jump around in some of these, okay? But we will come to that in chapter 13, okay? Pretty wild. Is that okay? Because I can pull a picture up that shows it better, but I'm not going to do it because I'll spend 20 minutes trying to get these slides to flip back up. Since I got this one working, let's just kind of stay with it. Okay, now another thing that's really cool about this, and let me point this out, that we discovered this system, we discovered the nervous system, how it worked, probably in the 50s, by studying these squid neurons in the spinal, which is like their spinal cord in squids. And so when we developed the computer, that y'all all have a phone, y'all all got, a home computer y'all looking at me with on here. Computers are man's attempt to mimic the animal nervous system. Okay, this kind of helps me learn it. So in other words, what are the components of the computer? Sensory input, keyboard, monitor, camera, right? Fax, a modem, Wi-Fi, whatever, hotspot. The CPU in your phone is the CNS, is the central nervous system, is the integrative, and your Apple programming makes your phone work the way it works. Zoom programming allows us to put all these pictures on the screen and look at each other, right? That is your integrative. And then the monitor that y'all watching me from is the motor function. The Canvas test y'all take or whatever, your printout, your email you sent me last night, all that is your motor function. So really, one of the coolest things to me is that the computer that y'all all should be somewhat familiar with is a man-made attempt to mimic the nervous system. And about 15 years ago, they developed maybe 10 or 15 years ago, they had a building full of computers, and they now have computers that can calculate and make decisions, action potentials at the rate we can. So there are computers that are smarter, that have more capacity than the human brain, but they're really big, and they're not as small as your brain. So that brain is still amazing in its ability to take in all this information and make decisions. Okay, pretty cool. I don't have time to show this one, but one of the coolest ones, I may try to get in tomorrow morning to show it. But I have a little video that demonstrates the 99% that's filtered out. And I may try to come in the morning. I think I can show it to y'all on a video, and then we can discuss it. But I think it'll be a good one to wake y'all up tomorrow on that. Now, how I said 99% is filtered out. It's a little experiment I can do to show you that. I might even do it after the break. Y'all, when we take a break, I may pull it up. It's on YouTube. Okay. All right. Now we're going to do a quick review of nervous tissue. But we've already seen this, right? The motor neuron is the functional unit of the nervous system. It has the cell body, dendrites, and axons, right? It has organelles inside of it. We know that, remember? Here we go. Remember, the dendrites and axons carry the electrical stimulation to the next neuron or to the target organ, as in skeletal muscle that we saw on the test we had yesterday or Friday. Talks about how slow it is to transport some stuff around. Not worried about that. There's the motor neuron. There's the neuroglial cells around it. Been there, done that. Here's our picture. So we're going to receive electrical stimulation on these dendrites in the form of what? Neurotransmitters released at a synapses, right? So we're going to come right back to that synapses that we saw on the muscle cell membrane. And that electricity is going to travel across the cell membrane. And if the stimulation is enough, it fires a electrical action potential that goes all the way down the axon, like we saw it going down the muscle cell membrane down into the transverse tubules, but we don't have that here. We have one long axon. That electricity reaches the end, and a neurotransmitter is going to be released at a synapses. So what we saw in the skeletal muscle is the way that very first part of skeletal contraction, the action potential, is the way the nervous system talks to its other neurons. Super important concept to get that today. Polio, real famous disease, right? Kind of like the COVID-19, but worse than COVID-19 of the 30s and 40s, was a virus that basically resulted in paralysis of the spinal cord. No cure exists, but polio can be easily prevented with a vaccination, right? And so Jonas Stark was the man who developed this vaccine, and I believe at a public lab. I think he may have been at a college or something, but he gave that to the world. So he did not profit off that. He did not sell money out. He just gave it to the world, and that cured one of the great plagues of the last century. And it really paralyzed children when they were young, and that's very, very terrible, right? And they had to be put in these iron lungs to breathe. They were having trouble even breathing. But what it did is it blocked the neurotransmitter junction and did not let the exponential occur. Okay. Other viruses, herpes, rabies, and other toxins also have the ability to invade into the nervous system. So polio is a really bad example of that. Here, once again, more verbiage than I need you to know. Receptive region that receive electrical impulse, the conductive region, and then the secretory region is the axon that's going to release that neurotransmitter. And the main one is still acetylcholine, but there's a whole bunch more we've discovered. Okay, now neurons come in different flavors. I'm going to just look at this real quick. The most common one that we saw, the one we looked at, y'all had on the test, was a multipolar neuron. So it had multiple dendrites and a single axon, and that is 99% of the neurons in the human nervous system. So multipolar are the common one. This is the one you're always going to see, and that's a multipolar, right there. Here comes Jasmine. Okay, so that's what we're looking at here. Now, others include bipolar. Now, let me make something very clear. Bipolar has nothing to do with bipolar disorder. Okay? So people always want to link that to it. This is simply one that has one axon and one dendrite coming out. And it is almost exclusively found in the eye and the smell receptors. Eye and smell. Okay? So eye and smell. And then we have another one that she's calling it now the pseudo unipolar, where only one fused axon extends, the cell body divides into two processes. And this is pain, touch, and pressure receptors, also pretty rare. Here's a picture of it. Excuse me, we'll see it in just a minute. So there we go. So there's the multipolar, the bipolar, sensory, smell, and we said vision. And then the pseudo unipolar, where it comes out one knob, but it splits into the dendrite and the axon. And this one is some of the touch, pain, vibration, probably that Meissner corpuscle or proscenium corpuscle may be associated with that. Now, backing up here, once again, this goes back to that theme I already said, that these neurons perform the three functions of the nervous system, right? Sensory input, sensory afferent neurons, that's a new word for you. Afferent means coming into the brain spinal cord. Interneurons making decisions, they're almost all multipolar. Look, all multipolar here. Sensory can be bipolar and pseudo unipolar, and then the efferents are mostly motor, multipolar, carrying information back out the body for a response. Once again, kind of going over those. Remember the three things the nervous system does: sensory input, integrative decision making, motor function. Okay, pretty wild. Once again, nice picture showing pictures of it. Okay. Now, specific neuron component groups, remember the CNS. Now, this is where we're going to not worry about so much about some of this. We're going to learn that we may see what are called clusters of neuron cell bodies called nuclei. Tracks are bundles of axons that are going to go up and down. We're going to learn a couple of nerve tracks in the nervous system, in the brain, I believe, in the next chapter. Okay. And then ganglion are just clusters of cell neuron bodies found out in the body. And nerves are just bundles of axons going to and from either the body to the spinal cord, or up the spinal cord to the brain, or vice versa, from the brain to the spinal cord out to the body. So when you see the words nerves or tracks, that's just talking about bundles of axons. Nuclei and ganglion are clusters of neuronal cell bodies. Some verbiage here. Neuroglial cells are going to be support cells, and we're going to now list the different neuroglial cells. These make all good matching and term questions, right? So we're going to see a lot of these support cells in multiple choice and maybe even a term. Notice that there are 4 we're going to learn in the CNS, that's central nervous system, and 2 peripheral nervous system support neuroglial cells. And we're just going to kind of fly through them. All right, the first one, and we're going to do the CNS first. The astrocyte, and this guy right here in the picture, large star-shaped cell, many processes terminating in what I call end feet. Look at what all it does. Remember I mentioned the other day how these neuroglial cells are becoming very important right now in biology. We're finding out that they're super important. These guys anchor the neurons and the blood vessels in place and helps define and maintain the three-dimensional structure of the brain. So these astrocyte cells are super important. Here's the blood vessel, look. And here are the neurons over here. So that's the neuron right over there, the orange or yellow, whatever, yellow. Transports nutrients and gases between the blood vessels and the neuron and regulate the extracellular environment of the brain. So the brain does not, motor neurons don't normally have nerves, blood vessels going to them. Instead, these astrocyte cells surround them and take the food out of the blood and the oxygen and get transported into the motor neuron. So this is a super important cell, and it also forms what's called a blood-brain barrier, which is a protective structure around the blood vessel capillary beds that makes it almost impermeable to most polar compounds and proteins. Okay, so this is the one I told y'all about that makes it very difficult to make pharmaceutical drugs that go into the brain, because see how tight these things are around this blood vessel? It makes the capillary bed less leaky, extremely tight to get things in and out. The only other place we see this in the human body is there is a blood testes barrier in the male around the seminiferous tubules that make the sperm in men. And that is thought to prevent your body from attacking sperm, guys, because it would be considered foreign DNA because of meiosis, because it changes our DNA code that we mentioned earlier. And also these guys repair damaged brain tissues. And so this is probably, the Alzheimer's is probably something wrong with astrocytes. Okay, would be a good guess. Not doing their job very right. So that's probably one of the more important ones. Okay, the oligodendrocyte is a very important one that produces a compound called, a lipid called myelin. That is what you're seeing here, this blue stuff over the axon. See the orange on there? That's the axon. And these oligodendrocytes are the blue one, and they form a layer, a covering over the axon. Now, the best thing, I'm just going to go ahead and tell you, the best way I can explain myelin is most of our axons and our nerves are covered with this layer of plastic, or not plastic, but lipid. But my metaphor is the plastic on copper wiring. If you ever done electrical wiring in a house, or a jumper or a extension cord, we've all seen an extension cord, or your phone charger. That white plastic over that copper wire keeps you from getting shocked, and it helps maintain the integrity of the axis potential, the electricity coming into your phone. Well, God has some wires that are unprotected, and those are the unmyelinated nerves that, guess what, transmit electricity slower than those that are covered with the myelin. So myelin is like plastic lining over electrical wiring. Now, one of the first houses me and my wife rented 30 years ago, or 25 years ago when we got married, 30 years ago we got married, but we're getting old, 31 years ago actually this summer. The old copper wires that we used to bring the phone in used copper. And a lot of people used to collect those glass coverings that are on the old railroad tracks of the electrical wire and run down the railroad tracks. If you've ever been around an old railroad track, there's usually what's like a phone line running down it. those are phone lines and Morse code lines from the cowboy days. And those glass insulators, they would wrap the copper around that glass because glass doesn't conduct electricity very well. And so people collect those. So when we was renting this house, well, no, we had new fine lines in this whole house, but all this ladies that we rented from, all of her worldly possessions were up in the attic, and she was like in a nursing home. I go up in the attic one day, and they still had the copper wires in there going wrapped around those glass. I mean, real copper wire running in that house going to the old phones, which we wasn't using anymore because we had new phones in there. But even that old farmhouse still had the copper wire in the roof where it came in raw, unprotected. Imagine a jump cable with no plastic covering, and that's an unmyelinated nerve. And they easily get shorted, and they can easily cause a fire too. So God likes to use the good extension cable with the thick plastic covering over it. Okay, and this is the cell that does that in the CNS. Now, I want you to notice something else here because it's going to be a test question, I believe. But notice how one oligodendrocyte may have 3 or 4 extensions, right? The myelin-producing cell in the peripheral nervous system is called the Schwann cell, and it completely surrounds and lives on top of the axon. And that's going to set up something really important later on when we talk about why, if you cut a peripheral nervous system nerve, you can reattach it, but you can't reattach the CNS nerves. So in other words, if you damage these neurons in your brain, they will not reconnect very easily because they don't have this tunnel for the nerve to go back down that's left behind by the Schwann cell. So I'm going to make a big deal about that when we get to those later, but I just want to mention I'll probably come back and look at this picture. Okay, so big one here. So electrodendrocytes make the myelin that covers and protects the axon and makes it fire more faster and more likely not to be grounded out. Okay, microglial cells, look at this one. Small, scarce cell, activated by injury into a wandering phagocytic cell. So this is probably a monocyte or some type of neutrophil that's gone to live in the CNS, since it eats bacteria, dead neurons, and other cell debris. So this is your intracellular cleanup in the CNS. So microglial cells are probably some modified monocyte. Isn't that pretty cool? That but they're like nothing else in the body because we don't see anything like that anywhere else. And then the brain has a epithelium on the outside, kind of a liner called epidermal cells that line all the cavities of the brain. It's even ciliated. It's a ciliated epithelium, line the hollow spaces in the CNS, the brain spinal cord, and manufactures and circulates the cerebral spinal fluid. So we actually have a circulation of fluid through the spinal cord called cerebral spinal fluid, and we'll look at that later on in the next chapter, I believe. But that is, there's an actual flow all the way around your brain, all the way down your spinal cord, all the way. It actually circulates. There's a little mini circulatory system, and this is the liquid that feeds and nurtures some of these cells we've been looking at. Okay, pretty wild. Here's a picture showing all these. Take a look. Here's the the astrocyte that forms the scaffolding, and these are the yellow are the neurons, right? And so they get food from the blood vessels and bring it in, feed these neurons. Here's the oligodendrocytes forming that myelin on the axon. Here's our cleanup guy, and here's the epidermal cells that line the cavities. All right, I'm going to let you catch your breath. There's a lot of new words here. I hope y'all looked over this just a little bit, but these are just some verbiage we need to know. Once again, all these are excellent test questions, right? Pretty cool. So these are pretty easy to see, right? Astrocytes, oligodendrocytes, microglial cells, and epidermal cells. All right, then we got the two of the peripheral nervous system are the Schwann cell and the satellite cell. The Schwann cell is going to be the oligodendrocyte equivalent. It's going to make the myelin sheath over the axons. And the satellite cell is very similar to the astrocytes, provides support function and supports the cells. And look at that, function not completely understood. Okay, here's what they look like. Here is look how the Schwann cells completely surround the axon. Right? Very cool. And then here are the satellite cells surrounding the neuron. Okay. All right, y'all been very quiet. So y'all got those, what, 7 cells? Y'all can handle that, right? Those are pretty easy. These are easy terms. Okay, now it's going to talk a little bit about myelin, that myelin sheath we're talking about. That's a lipid sheath, protective layer, and they even use that. It's a lipid content that forms a sheath, insulates the axon, prevents ion movements like rubber around copper wire, increases the speed of conductivity. Myelinated axons have action potentials that run at 15 to 20 times faster than unmyelinated. Now, when we're dissecting the cat and with Angel next month, or whenever you take AMP2, if you see a white line going down an arm or leg, that is a myelinated nerve. So the myelinated ones are shiny, and unmyelinated nerves are not real pretty and shiny. So they are slower because they don't have the Schwann cell lipid myelin covering over them. Okay, that's kind of important to know. Now watch this. On the outside of the Schwann cell, we get a connective tissue surface called a neurolimia that forms this protective covering around it. Okay. Now look at this. Oligodendrocytes have multiple processes that do multiple axons, whereas the Schwann cell only does one axon at a time. Myelination begins as early as fetal development, and very little myelin in the newborn. Matter of fact, one of the reasons children are very uncoordinated is their nerves are not myelinated out in the legs and arms, so as they're growing. But I want you to look at this neurolimia right here in this picture. See this right here? This is a connective tissue layer outside of the myelin. Here's the myelin, and here's the axon. Okay, so when you cut a myelinated nerve and all the axon rots out, the stub will regrow. But if it don't hit that tunnel, then that nerve will not reconnect. So what we can do is we have a tunnel left, and we'll see in just a second, after you cut an axon of a peripheral nervous system nerve that has the Schwann cells. And that tunnel is what a neurosurgeon reconnects that nerve stub to, thereby regrowing our nerve. We can reconnect arms and fingers and legs and stuff if they get cut off and are not destroyed in the accident. We'll talk more about that. There's some slides of that coming up in a minute. Whereas the oligodendrocytes multitasking, and there is no neurolimia. So is that clear? There is no neurolimia on the outside of the central nervous system covered axons covered with myelin by the oligodendrocyte. So that's going to be a big deal in just a minute. I believe it's a question on our test. So this neurolimia, only found in the peripheral nervous system, leaves a tunnel for the nerve to go back down. Okay, the space in between the Schwann cells is called the nodes of Ranvier, and then the whole length at which the Schwann cell covers it is called the internode. And so the electricity is going to jump from node to node, and it is extremely, like 20 times faster than an unmyelinated nerve. Now, I'm not even going to get into the physics of that. I explained it once on a test when I took it. I'm not going to expect you to know that physics answer. Just know that myelinated nerves are faster. Okay, and I'll be thrilled. And here it talks about it. White matter are those that have myelin on them. Gray matter, gray nerves that are not white and shiny are unmyelinated. Okay, pretty cool. So when you talk about gray matter, you're talking about what? Unmyelinated neuroaxons, and white matter are myelinated axons. You can see the unmyelinated here, and then the myelinated ones are going to have the Schwann cell around them. So that one's all on around that one there. Kind of weird picture. Okay, now here's where it gets about this regeneration of a nerve. If you have a myelinated nerve like this one, and this actually happens, you cut your finger off. I have a friend of mine back about, oh man, this was like when I first came to work, maybe 25, 30 years ago, and he professionally played saxophone. He had a very successful business in North Mississippi. His hobby was woodworking, and he had a bandsaw in his woodworking part of his house. He probably had a 5,000 square foot house. And he had this is back before everybody had a phone. He had an intercom system in his house. So he could play music in his house. He could hit a button and talk to his wife in the kitchen. So he's playing some music, and he somehow run his hand across the bandsaw and cut all 4 fingers off his right hand, like right here. Now, my wife's family are these people that when the crap hits a fan, they freak out, and they're very useless in an emergency. Y'all know who I'm talking about? Anybody got family members like that that scream and holler and maybe, and I'm not against prayer, but let's do prayer and action too. You know what I'm saying? But they just freak out. Well, his wife was one of these proactive, probably should have been a nurse. She heard him screaming on the intercom. She came down, put a towel around his hand, picked up his fingers, put them in a bag of ice, threw him in the back seat of their SUV. They lived south of Batesville, drove right past the Batesville Hospital, didn't even think about it. Drove right past the San Antonio Convalescence Home. Drove right past Baptist DeSoto. It wasn't even there yet, but we'll pretend it was. And went straight to the med. There's only one trauma 3 in North Mississippi, and it's the med. And they reconnected his forefingers with microscopes, reconnected the nerves and the blood vessels. And I saw him play that saxophone 6 months later. Give another story. Had a girl in my night class, on a Monday night class, just a few years after that. Sweet girl, be like one of y'all that's blowing this class away. She had like an A and everything, and she was probably the 25, 26-year-old lady, and definitely smart enough to be a nurse. Her husband worked in Tunica for a farmer. They're very poor, and he was a laborer for a farm. Didn't own it. He was a farm laborer. I was raised on a small farm. We had like 8 people worked on my dad's farm. We can't pay them well. They had no health insurance. It's just really a tough life, living paycheck to paycheck. And that girl was about at midterm, and she had an A, and she didn't show up on Monday night. The next Monday night, she walks in, and she looked like she hadn't took a bath, hadn't slept in 3 or 4 days. And I'm like, what happened? And she said, well, my husband was working last Monday right before I left to come to class, and he told the guy driving the tractor, whoa, and he thought he said, come on, and he backed the tractor into his finger and cut his thumb off hooking up a do-all or a tractor part. And I said, oh my gosh, what happened? They said, well, they called me and they took him to the Tunica Hospital. And this is before the casinos, okay? This is when Tunica Hospital was like, well, they're third world countries with better hospitals than Tunica, okay? He gets in there. She said, I get there, I'm in the ER, and about an hour or two, this doctor comes out, and he'd been in surgery. You can tell, you know, like in the movies, walked down and sat down to me and said, hey, your husband's thumb was cut off. And I quote, this is the quote, and my brother was not a lawyer yet. So listen to this quote. I just reattached your husband's thumb. I've always wanted to do that. And all I could do, Heather, was like, call a lawyer. I mean, I've lived like digging names out of my lawyers, giving it to her. And I just said, okay, this is like 5, she's always early. This is like 10 minutes before class. And I said, okay, I just called Roe. I want you to get in the car. What does his thumb look like? Well, it's swollen up and it's blue and it's black. And I said, get him to the med right now. Just go get him. You're here. I'm not going to count you out. So get to the med. She called me back the next day. They had to amputate his thumb. They didn't even reconnect the blood vessels half right. No nerves. The guy just sewed it on like it's going to regrow. Okay. You understand they would own that Tunica Hospital today if they had sued. Okay. Tremendous. I mean, idiot. That is the one phrase you would never want to hear from a doctor. I've always wanted to do that. Okay. That's just, I just hear that's what they call the rainmaker in law school. So there was a 25-year-old man permanently disabled now because of that. Okay. Y'all seen the ones on the TV? There's been a bunch of them, you know, they probably the one that comes to my mind that's the most interesting was this young boy was home by himself running a tractor. His parents don't know where to crap his tractor. He was like 15-year-old running a corn picker. And early in the morning, I've been there, the corn gets hung in the tractor. So he left the tractor full throttle and got out and started pushing it with his hand and got his hands on the combine, and it ripped both arms out and threw him in the cornfield. So he's walking there now with his brachial artery about to bleed to death. He goes into his house. You Google this. This is a real famous one. And he gets on now look, this is before everybody had cell phones, right? He's got no hands, and he goes into the house, opens the door with his mouth, knocks the phone off the wall, dials 911, gets down to the receiver and says, help me, help me. And this wonderful 911 operator, like, settle down, where are you at? Give me your address. Okay, the ambulance is on its way. And she said, where are your arms? He said, I don't know, they're in the cornfield. And listen, the woman told him to get into a corner and push as hard as he can as if you're saving your life. And so he put himself into a corner, compressing his shoulder. The EMTs got there, stabilized him. And as they're loading him on the ambulance, they said, we better go kill that tractor because it's still running right there by the house. They go out there and his 2 arms are hanging in the corn. And I saw him like 4 months later, open the ER doors to leave the hospital. He had 2 permanent scars here and here, even turned them into barbed wire tattoos. And kind of a neat story about the guy. He was an atheist at the time. The people were not religious. And he got thousands of letters, God was with you and all this stuff. And he was real negative. He's like, well, if God was with me, why would he with me when my arm got ripped off? Which is a really good question, by the way. And I'm not going to argue with God about that because I think bad things happen to good people all the time. And that's not God. That's just the devil. That's just my thought. But then after all the letters, he ended up becoming a Christian after so many people kept writing him over the years. Okay, but he's got the barbed wire where he has the surgery where both arms are reattached. I was scared he was going to put them on backwards too. When he opened the door, I kind of had it fringed in case they put them on backwards. But they got the right one on the right, left on the left. So if you cut on a hand, fingers, toes off, get them, pick them up, put them on ice, and get to the hospital quick. Because watch, here's what happens. The tunnel, the axon dies, but the neurolimia leaves a tunnel for the new nerve to grow back down. And if it does, it will reconnect. I have a very good friend of mine who was he'd never drove tractors, and he bought a lot outside town here, and he was driving a tractor on the gravel road and lost control and flipped it off an embankment, and it rolled over on him. And he luckily, about an hour after laying on the tractor, they found him. They had to fly him with the wings of life to Memphis. When I got up there, I actually drove the wife, a real good friend of ours. I drove her to the hospital, doing about 100 miles an hour, and we got there just right behind the helicopter. And so we were there, and after about an hour or two, they were working on him. The surgeons of whoever, the healthcare people came back to her and me and said, okay, were y'all at the scene? And I said, yeah, we saw it. And they go, what burned him? And we looked at each other and said, he didn't get burned. She says, no, these are burns. What burnt him? And they took me back there and showed me his leg. He was out. And y'all, he was not burned. The pressure of that tire, that truck, the tractor on him squeezed the cytoplasm out of his cells, y'all. And he was popped up bubbles that they thought were burns, but just the squeezing of the body, of the pressure on his leg made them pop up, made bubbles pop out. And he could not feel his legs for like several months, but they regrew. But he was in great shape. I mean, he was in unbelievable physical shape. One of the most fit people I know, where it would have probably killed me. But anyway, but he's still doing well today. But he had to have some knee surgery, I think, some ankle, tore some ligaments and stuff. So you can regrow peripheral, but we cannot reconnect the CNS because it doesn't have that little tunnel. So we cannot do a brain transplant like that now. We can't reconnect the brain after a gunshot wound or cancer. But very cool questions. And there's a question on your test about regeneration of nerves. Okay. Specifically the what? PNS can regenerate because of the neurolimia leaving that tunnel for that nerve to grow back down. Here's what some brain tumors look like, and you can see on this MRI. This was what was this one? Anyway, this is the most common type here: astrocytoma. Astrocytes all messed up, forming a tumor. And of course, brain tumors are very, very bad. Yeah, because a lot of times if they're metastasizing, they're hard to stop. Okay, now we're going to go back to our good old electrophysiology, and they go over the axe potential again. And I'm not going to think I'm going to try to do it quick. May show the little video on it, but once again, they're going to see this, and this is a lot of repeat because we're going to talk about the excitability of a neuron, right? That local potential, the resting membrane potential, and then that action potential. And so she talks about how there is an uneven discharge of neurons, of electrolytes. Remember, we already know that. Sodium on the outside, potassium on the inside, and because the potassium can leak out easier than sodium leaks in, we get that resting membrane potential, right? Voltage of, and now it's 70 millivolts in the neuron. Okay, so remember that we have a negative 70 millivolt across the cell membrane of the axon. Okay, and that's mainly due to what? Potassium leaking out. Remember the sodium potassium pump, and a lot of y'all left this one blank. I'm going to say about half of y'all nailed the axe potential and the muscle contraction. About half of y'all, I would not base my life on what y'all, if y'all could explain to me how muscle contract. They were sketchy, and I'm using that word very loosely. Okay, they were bad. Okay, and y'all, that's why some of y'all didn't do well. Y'all did not learn the nerve muscle contraction and relaxation very well. But y'all may have done a little bit better on that one than the axe potential. So we'll play the video again in just a minute, let y'all see it again. But that is our resting membrane potential, right? And that is maintained by, we can try this. Maybe this will help. Let's see if this is any good today. See if it's going to work. Don't have sound.
The human brain alone contains about 100 billion nerve cells.
Let's take a look.
Called neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks.
Okay, now all that is to set up the action.
Thus, the pumps help to maintain the resting membrane potential.
Okay, so that's a little bit helpful. Maybe that's a little too, sometimes those videos go a little bit deeper, but that's all showing you how that resting membrane potential exists. So now that we can what? Have that electrical event called an axe potential as we get that wave of depolarization traveling down the axon. So this is just talking about those different gates that she just talked about in the video. Okay, and remember we have the leaky ones, we have ligands that what? Ligand means what? A neurotransmitter binds to it to open. Voltage gated means that they pop open when they get shocked. Okay, and then others are the mechanoreceptors, when they get stimulated or stretched, they open up. And that's how we do touch and sensation. Okay, and it talks about the sodium potassium pump maintaining that gradient of high sodium on the outside, which is a positive ion, and high potassium on the inside, which is also a positive ion. And then depolarization, here's the pictures. We already did this. So I'm going to show you the video. Again, we're going to take a break here in just a minute. It's not quite 9. But when you have a depolarization, right, a stimulation, the sodium channels open up. And if we reach the threshold, right, then actually here it is hyperpolarizing, right, meaning going the wrong way. That means we got hyperpolarization is the loss of positive charged ions. But depolarization is when it goes positive, that's going to lead to a axe potential. So depolarization is going toward the axe potential. Hyperpolarization is making it even more difficult to fire an axe potential. So depolarize is taking it up. Repolarize brings it back down to minus 70, and hyperpolarize is taking it down to minus 80 in this picture. Couple of cool ones here. Lidocaine is used during dental procedures and surgery, right? Blocks voltage gated sodium channels of the neurons, preventing an axe potential from depolarization from occurring. Okay, it's non-selective, right? So it can temporarily paralyze the muscle, so you get the droopy face, right? And the drool that you can't control after having oral surgery. So lidocaine stops voltage-gated sodium channels, so you can't have an axe potential. Okay, we already said depolarization, hyperpolarization. A lot of repeating on these slides. And you get a graded potential. Okay, let's take it. We'll go and look at that a little bit more. Actually, let's watch her now. I'm going to play these because some of y'all need this. She does a really good job here walking you through the axe potential. Actually, I hit the wrong button. Sorry. She's got a couple of slides here. I think they're pretty good.
Before any stimulation, the neuron is at rest. Recall that the resting membrane potential of a typical neuron is negative 70 millivolts. This potential depends on the distribution of sodium and potassium ions across the plasma membrane and their movement via leak channels and the sodium-potassium ion pumps. Stimuli are detected by the receptive region of the neuron, which generally consists of the dendrites and cell body. When a neuron is stimulated, its resting membrane potential changes because ions begin to cross the plasma membrane through gated ion channels. If ligand-gated sodium ion channels open, sodium ions follow their electrochemical gradient and enter the cytosol. As the inside of the neuron gains positive charges, it becomes less negative, a change called depolarization. If ligand-gated potassium ion channels open instead, potassium ions follow their electrochemical gradient out of the cell, and the cell loses positive charges. This causes the membrane potential to become more negative than it is at rest, a change called hyperpolarization. Hyperpolarization can also be caused by the movement of negatively charged ions, such as chloride, into the cell. Small local changes in the membrane potential are called local potentials or graded potentials. They can be depolarizing and therefore cause positive charges to enter the cytosol.
That's what we saw with the muscle cell
potential
membrane.
less negative. Alternatively, they can be hyperpolarizing and make the membrane potential more negative. Local potentials also vary in strength, depending on the length of stimulation and the number of ion channels that open. We can compare local potentials to the ripples caused by a pebble thrown into a pond.
That's a good metaphor.
A larger stimulus, or pebble,
On the
will
right,
cause a larger ripple effect. And a smaller stimulus, or pebble, will cause a smaller ripple effect. Another important feature of local potentials is that they are decremental, meaning that they weaken as they get farther away from the source of stimulation, and so are only capable of traveling over short distances. If we use our pebble analogy again, as ripples move away from the point where the pebble hit the water, they diminish in size and eventually disappear. For this reason, local potentials cannot be used for long-distance signaling. A single neuron can
What's
receive
this?
many incoming stimuli in the form of depolarizing and hyperpolarizing local potentials. These local potentials combine as they spread across the membrane of the neuron. The sum of these potentials determines whether or not an action potential is generated. We will discuss that effect in the action potential animation that follows.
okay, now what do y'all think about this? This is pretty fascinating. And I think the part here that y'all haven't seen before is that a neurotransmitter can be inhibitory. You follow me? So some of the neurotransmitters hyperpolarize instead of depolarizing. So let's say that this is a stimulation telling you that somebody dropped on your, you dropped 500 pounds on your toe. Then that would be enough green to trigger an action potential that would tell my brain, hey, something's going on down here. A fly crawling on my face while I'm sleeping that doesn't fire an action potential, then would be enough of the red of preventing it from firing. So this explains why some nerves, like you don't feel an insect crawling across your body because it doesn't stimulate a receptor. But some neurotransmitters are inhibitory. They're not all are excitatory. Okay, let's watch one more segment of this and we'll take a break. Give y'all a moment to catch your wind here. But she does a really good job. Now watch this. We're going to see that the sodium channels and potassium channels here, specifically the potassiums are either open or closed, but the sodium channel is going to have three states. Look at this: a resting state when it can't be fired, an activation state when it's open, right? And this inactivation stage when it can't be fired. So here's ready to fire, open, and then closed, but cannot be reopened. It has a little refractory period before it can fire again. And so sodium channels have a weird little thing going on there. Let's watch one more segment of this video, and then we'll take a break.
Before any stimulation, the neuron is at rest. Recall that the resting membrane potential of a typical neuron is negative 70 millivolts. This potential depends on the distribution of sodium and potassium ions across the plasma membrane and their movement via leak channels and the sodium-potassium ion pumps. Stimuli are detected by the receptive region of the neuron, which generally consists of the dendrites and cell body. When a neuron is stimulated, its resting membrane potential changes because ions begin to cross the plasma membrane through gated ion channels. If ligand-gated sodium ion channels open, sodium ions follow their electrochemical gradient and enter the cytosol. As the inside of the neuron gains positive charges, it becomes less negative, a change called depolarization. If ligand-gated potassium ion channels open instead, potassium ions follow their electrochemical gradient out of the cell, and the cell loses positive charges. This causes the membrane potential to become more negative than it is at rest, a change called hyperpolarization. Hyperpolarization can also be caused by the movement of negatively charged ions, such as chloride, into the cell. Small local changes in the membrane potential are called local potentials or graded potentials.
And
they can be depolarizing and therefore cause positive charges to enter the cytosol and make the membrane potential less negative. Alternatively, they can be hyperpolarizing and make the membrane potential more negative. Local potentials also vary in strength, depending on the length of stimulation and the number of ion channels that open. We can compare local potentials to the ripples caused by a pebble.
she kind of said this earlier, so this is a little bit of repeat. But if you get enough of the ripple, then that will trigger the whole axon to fire. Look, and that's where we're going to get to. So we haven't done ax potential yet.
Or pebble will cause a smaller ripple effect. Another important feature of local potentials.
We've kind of hit that. So that kind of repeats the last one we watched. And that's just summation of those can lead to an ax potential. Enough on that one. Okay, hold on. Let's watch this and go over on the road here, and we'll take a break. We're pushing y'all. But here's the one I was meant to do.
As we learned previously, a single neuron can receive many incoming stimuli in the form of depolarizing or hyperpolarizing local potentials. In a process called neural integration, all of these incoming stimuli are combined. If enough of the stimuli are depolarizing, their cumulative effect will reach the trigger zone.
Watch this. This is a big one.
This zone consists of the axon hillock and the initial segment of the axon. When the trigger zone depolarizes to threshold, it generates an action potential. An action potential is a large, uniform depolarization followed by a rapid repolarization. Action potentials are all or none events. In other words, if an action potential is triggered, it will occur and will propagate down the axon. If, however, the trigger zone does not depolarize to threshold, no action potential will be generated. You can think of an action potential as a bullet being fired from a gun.
That's a good metaphor.
If you pull the trigger with enough strength, the gun will fire the bullet. Once the trigger is pulled, the shot cannot.
Can't take that shot back. You can't.
In a similar way, an action potential, once fired, will rapidly travel down the axon without losing any strength and cannot be reversed or stopped. Let's now examine the events of an action potential more closely.
What's this?
We begin with the axolemma and the trigger zone depolarizing due to the summation of local potentials. It depolarizes from the resting potential of -70 millivolts to a threshold potential of -55 millivolts. At the threshold potential of -55 millivolts, voltage-gated sodium ion channels open. Sodium ions quickly rush into the axoplasm, driven by their electrochemical gradient, and cause a rapid depolarization.
All the way down the axon.
30 millivolts. At the peak of depolarization, the voltage-gated sodium ion channels inactivate, and sodium ion influx stops. If we look closely, the sodium ion channels have two gates, one called the activation gate and one called the inactivation gate. The gate that closes and plugs the channel at +30 millivolts is the inactivation gate. At the same time, voltage-gated potassium ion channels open and potassium ions exit the axoplasm, moving with their electrochemical gradient. Now the cell has stopped gaining positive charges and is losing positive charges instead. This will cause it to return to a more negative membrane potential, a process called repolarization.
Back to minus 70.
As repolarization approaches the resting membrane potential, sodium ion channels switch from their inactivated state to their resting state by closing their activation gates and opening their inactivation gates. At the same time, potassium ion channels begin to close. Potassium ion channel gates are slow to close, and potassium ions continue to leave the cell past the resting potential of negative 70 millivolts. As a result, the axolemma hyperpolarizes to about negative 90 millivolts. Finally, when potassium ion channels return to their closed or resting state, the axolemma returns to its resting membrane potential, maintained as always by the sodium-potassium ion pumps and leak channels. Action potentials provide a fast and efficient mechanism for sending signals down the axon as the neuron transmits a stimulus to another neuron, muscle cell, or gland. In the next animation, we will discuss how the action potential is propagated down the axon.
All right, guys, that's a little bit more detail on the action potential. And we've done seen this on a test, so it shouldn't be like new stuff there, because I mean that's the deal. That's how the brain works. And let's take a quick break, and I'll try to call roll. We got a few folks not here, so let's y'all take it. I'm gonna stop the video recording, so we can just hang on. We'll take a break for a minute. So let's take a break. I got about 7 after. Y'all take about 5 or 6 minutes. Okay, and we'll wake up some people. I don't know if everybody's logged in here. I've got a thin crowd today.
I have a question, Mr. Robison.
Yes, please.
So, I think the video answered my question, but I was wondering about hyperpolarization and how, like, when it's necessary, like when it's happening.
That's just when it goes back to normal. It just accidentally hyperpolarizes. That just happens, but it's very quick and it's back to 70. So it's almost.
So is that like really? Does it do anything to the? It just
makes it a little more unlikely to fire an action potential.
Okay.
So it really prevents it from firing for a little while, like it's resting.
Right. It's just because the potassium ion channels are slow to close.
Yep. Yep.
Okay. Thank you.
But now remember, the intensity of a stimulation is how many action potentials fire per minute or per second. So think about that. So it's kind of like Morse code, right? Click, click, click. The faster the click, the more stimulus. Pretty wild. Yeah, take a break here and I'll call the roll here. We got a few not here today. If everybody would have showed up, I wouldn't have had to call roll, man. I'm picking. Y'all been awful quiet today. Anybody got any questions while we're waiting on everybody to get back? Anybody? This is pretty wild, isn't it? I think this shouldn't be that hard for y'all because we kind of hit the exponential. And y'all, most of y'all got that right about the sodium potassium. That's about the depth I want you to know. But this just kind of give you a little more information as to what's going on here. And I think the only thing new is that I think the sodium channel having the 3 stages is kind of interesting. So it can't fire again in that period. So we have a refractory period there and talks about that. Here's kind of showing you what's going on. And there's what's happening with the different points. So in this period right here, look right here, see, in this refractory period, the sodium, they can't fire another exponential because as long as that gate's in that state, it won't fire. That's kind of a cool concept there. All right, I'm trying to look at that. These chapters are pretty crazy. So we got the nervous system. I think the brain is the next chapter, and then there's one on the CNS chapter. Then the 14, like I said, is pretty short, but 11 and 12 are like crazy long. 12 is even long. It's really long. All right, let's start back. I got that's about 7 minutes. So anyway, just looking at this, I'm going to go on through this, let you watch our video again here at this next one. But this is just showing the different stages of what's going on with sodium potassium channels during the action potential, during the peak here. And I think that's pretty cool. Action potentials are all or none, right? And they're all the same, right? So there's no difference between them. It's just the number of action potentials determines the strength and frequency, you know, and all. So it's not, there's not a high, low. It's all or none. You either get an action potential. I love the bullet metaphor. You either shoot to a gun or you don't. Bullet fires or it don't. If the bullet fires, it's going to go all the way down. Okay, nothing much here. Talking about conduction of that down to the action potential. Here's showing it again, showing the event on the picture that she showed in the video. And that is, so the action potential is that depolarization going all the way down the axon until it reaches what? The trigger zone down to end, or at the synapses where we're going to release a neurotransmitter. So that's just exactly what we'd already looked at 100 times. Let's let her wrap it up. I think this is the last one on
Neurons
her action
receive
potential.
stimuli from other neurons or from sensory stimuli in the internal or external environments. If the incoming stimuli are significant enough, they depolarize the neuron's trigger zone to threshold and an action potential is generated. The action potential is quickly propagated down the axon and reaches the axon terminals. At this point, synaptic transmission occurs and allows the neuron to communicate with other cells, including other neurons, muscle cells, or secretory cells inside glands. The location of communication between the neuron and its target cell is called the synapse. The most common type of synapse in the nervous system is the chemical synapse. As the name suggests, these synapses use a chemical known as a neurotransmitter to transmit the signal from the initiating presynaptic neuron to the receiving postsynaptic neuron. Over 100 neurotransmitters are used by our nervous system. Examples include acetylcholine, dopamine, norepinephrine, and serotonin. Remember that there are 3 parts to a chemical synapse. First is the axon terminal of the presynaptic neuron, which contains synaptic vesicles that store the synaptic cleft. Let's now look at the events that happen at a chemical synapse between 2 neurons. First, an action potential arrives at the axon terminal of the presynaptic neuron. The resulting depolarization in the axolemma opens voltage-gated calcium ion channels. Extracellular calcium ions enter the axon terminal following their electrochemical gradient. This causes synaptic vesicles to fuse with the presynaptic membrane. The vesicles then release neurotransmitters into the synaptic cleft, a process called exocytosis. Next,
Okay, I've got something going on here. Hang on. Why it's doing that?
the transmitter molecules diffuse across the synaptic cleft and bind to receptors in the postsynaptic membrane.
This is going over what we already saw in muscle.
These receptors can be ionotropic, meaning the binding of a neurotransmitter directly opens an ion channel, as seen here, or metabotropic, meaning that it opens ion channels indirectly. The resulting movement of ions across the plasma membrane will cause a change in the membrane potential of the postsynaptic cell. The average neuron can form synapses with about 1,000 other neurons, thus forming a complex neural network. Chemical synapses provide the means for transmitting signals within that neural network. The strength of the signal varies depending on the amount of neurotransmitters released and the frequency of stimulation. The effect on the postsynaptic cell depends on the types of receptors present in the postsynaptic membrane.
Okay, so summary. Everywhere an axon touches another what? Dendrite cell body, or in the case of muscles, a muscle cell, a neurotransmitter, the way that they transmit that information is through what? A neurotransmitter being released at this gap called the synapses. I would imagine there's going to be a question on the test about synapses, don't y'all? But that's kind of big. And we're going to look at about 10 or 15 of these neurotransmitters where I got to know them all because they're so vague. They have multiple functions, but we'll mention a couple of them in a minute. So I think that's a pretty cool video showing you how neurons communicate with each other. And that is through this gap called the synapses with the release of that neurotransmitter that we saw in action of the muscle contraction. Okay. I thought we about beat this thing out. Let's see what she does here one more time.
Once an action potential is generated at the trigger zone, the impulse propagates like a wave down the length of the axon. Action potentials are non-decremental, which means that they do not lose strength as they travel. This is possible because each action potential triggers a new action potential farther down the axon. So in reality, a nerve impulse is not one action potential, but a wave of many consecutive action potentials. A helpful analogy is a row of dominoes. When the first one is flipped over, the next one falls. And once they start to fall, the process sustains itself until the end. The transmission of an action potential down an axon is known as propagation. It occurs from the trigger zone and moves toward the axon terminals at a rapid, constant speed. Propagation always occurs in one direction because of a phenomenon called the refractory period. This period is a brief time during which the axolemma that has just produced an action potential is either unable or less likely to generate another action potential. Recall that immediately after the rapid depolarization of an action potential, voltage-gated sodium ion channels are inactivated. Sodium ion channels have two states in which the channel is closed, the inactivated state and the resting state. When the channels are either activated or inactivated, they are not able to open again to produce another action.
So there's that period where you can't fire again.
To their resting state.
Then they can fire again in the resting
state. This is
state.
called the absolute refractory period. Following the absolute refractory period is the relative refractory period, during which the axolemma is hyperpolarized and therefore farther away from threshold and less likely to produce an action potential. Now let's take a look at how the action potential is propagated down the axon. First, local potentials depolarize the trigger zone and cause an action potential to be generated in the initial segment of the axon. As this initial segment depolarizes, positively charged sodium ions spread to the next segment of the axon and depolarize it to threshold.
Sodium's coming in.
When the axolemma of that second segment reaches threshold, a new action potential is generated. The depolarizing current then spreads to the neighboring segments of the axon, with the previous segment in the refractory period and therefore unresponsive to stimulation.
That's why you don't get an action potential going
Only
both
the segment
ways.
farther down the axon will respond by depolarizing to threshold and generating an action potential. This process then repeats down the length of the axon until it reaches the axon terminals. The mode of propagation we just discussed is called continuous conduction. It happens in unmyelinated axons. There is a second mode of propagation called saltatory conduction, which allows for faster and more efficient.
That's a good term.
conduction.
Saltatory is when you have an
It
action
occurs
potential
only
down a
in
myelinated nerve.
axons. Let's recall what a myelinated axon looks like. The myelin creates insulated sections of axolemma called internodes. The gaps between myelinated sections are called nodes of Ranvier. In a myelinated axon, action potentials are generated only at the nodes of Ranvier. Myelin is an excellent insulator, and it allows the sodium ions in the axoplasm to reach the next node of Ranvier and depolarize it to threshold. To better understand the difference between continuous and saltatory conduction, think of crossing a room by taking many small steps, analogous to continuous conduction, or by taking a few large jumps, as in saltatory conduction. Since the action potentials in saltatory conduction jump from one node of Ranvier to the next, propagation is much faster and fewer action potentials need to be generated.
All right. I think she's got one more. My goodness. Let's see. Let's see. Is that the one? I think that's the one we just watched, isn't it? Let me make sure I didn't get.
Once an action potential is generated at the trigger zone,
Yeah.
the impulse propagates.
I think that's about it on them, I hope. About videoed out. So that's just showing it to you again. I thought that was pretty good. Last little video showing that one more time. It's talking about how this is just nothing, how you can short circuit a thing. Myelin prevents or insulates it. Look at this. There are a couple different types of factor of these axon fibers. Type A fire at 120 meters per second or 250 miles an hour, and they have a diameter of 5 to 20 micrometers. So these are very fast ones, skeletal muscle and joints. Type B is slower conductive at 15 meters per second, and these are myelinated, but they're only 2 to 3 micrometers. And look at this next one. In class C, smallest diameter fibers, unmyelinated. These are unmyelinated, like pain receptors, temperature, and certain pressure receptors, and they only go 0.5 to 2 meters per second, or 1 to 5 miles an hour. So now here's another one. If you ever done speaker wire, you may know this, but if you get into speakers that have copper wire, the thicker the wire, the better the transmission. So thicker wires are better. Like y'all may have heard of these monster cables you can buy at Home Depot or electronic places. So they're really good for speakers, but for direct TV and digital, it doesn't matter, because as long as you have a signal, it doesn't matter. The thickness doesn't make it any better. Okay, but it's kind of wild. But so thicker fibers fire faster. And the myelin, you can tell, like myelinateds go, and I'm no mathematician, but look at this. If you got one firing 120 miles per, 250 miles an hour, and this one's at 1, then that's 250 times faster, right? And even at 250 and 5, that's 50 times faster. That's pretty freaking amazing to me, the difference. Multiple sclerosis is a terrible autoimmune disease where your myelin is eating off your nerves. So the myelinated sheath is destroyed, rendering that body part numb, or no sensation or inability to move a body part, paralysis. So MS is a very bad autoimmune disease, eating that myelin sheath off. Here's another picture showing it all again. Then we'll look at then we talked about the different synapses. The most common one being the where we're going to produce a neurotransmitter, right? We talked about that. So basically, here's some verbiage that drives people crazy. Well, you have a synapse, the one sending the impulse is the presynaptic neuron. The one receiving the neurotransmitter is the postsynaptic neuron. Why we got to name weird words that scare us, right? So synaptic transmission can be chemical, and that's the main one we see, but there are a couple electrical transmission, and that was that gap junction in cardiac muscle. So in electrical and cardiac and smooth muscle, ions travel through the gap junction. Check it out. And you have ion that can travel back and forth between cells, and that's how you get that rhythmic cardiac muscle contraction or that rhythmic bubbling of the stomach. So that is and there are also electrical in the brain, but she's very vague about that. So some of the axons up in the brain are electrical, but it's not really electricity arcing like a spark plug or lightning. It is ions, which are charged, traveling through these gap junctions. Remember, one of our junctions between cells that allow for electrical synapses. And that was not in the old book that we taught out of. So I do think that's worth mentioning. The one we've been talking about now for 2 or 3 days is chemical. And that chemical is a neurotransmitter, right? We talked about. Once again, can we make it a little more difficult? Synaptic vesicles are the little things with the little bags with neurotransmitters that are released in the gap, now called the synaptic cliff. Then we have the, there we go. So here's the, there we blow it up. There's a synaptic vesicle. Here's the gap. The neurotransmitter is going to be released. It's going to go across and bind to receptors. Now here's the part that's kind of interesting. In skeletal muscle, they were stimulatory, but some neurotransmitters prevent action potential. They hyperpolarize the membrane. So not all neurotransmitters are stimulatory. Some are inhibitory, and some of those that are the pain neurotransmitters stop action potentials from firing, so you don't feel somebody operating on you. That's pretty cool. But just kind of looking at those. Do we want to watch it? We might as well. Do you want to see a little video on synapses? We might as well.
Neurons receive stimuli from other neurons or from sensory
We've kind of seen this before. We'll do it one more time.
External environments. If the incoming stimuli are significant enough, they depolarize the neuron's trigger zone to threshold, and an action potential is generated. The action potential is quickly propagated down the axon and reaches the axon terminals. At this point, synaptic transmission occurs and allows the neuron to communicate with other cells, including other neurons, muscle cells, or secretory cells inside glands. The location of communication between the neuron and its target cell is called the synapse. The most common type of synapse in the nervous system is the chemical synapse. As the name suggests, these synapses use a chemical known as a neurotransmitter to transmit the signal from the initiating presynaptic neuron to the receiving.
I think we got this. I think we have seen this 100 times. I'm going to skip a little bit of this.
Over 100.
We've already seen that. We know what's going to go on there. We've done this in muscle, right? I think we got it. I'm going to move on. Try to get through this chapter today. I think y'all got that. Okay, we've been over that 100 times. Saw that other day. Here it's getting into a little bit more of the detail that I want you to know about, but some are inhibitory that prevent action potentials. Like I said, some are stimulatory. Just gonna see if there's any. I don't think there's anything in here I need you to see. Let me just look.
Recall that all action.
That's just showing it to you. Look, so you got IP inhibitory and excitatory, right? So what happens is, this goes back, y'all seen the old commercial when you're trying to decide, like, let's say somebody goes, hey, let's go out clubbing tonight. And the little devil pops up on Heather's shoulder and says, ooh, go Heather, go have fun, get drunk. And then the little angel appears like, don't go, you need to study for your A&P final on Thursday, right? So your brain is always getting competing information, right, that says fire or not fire, right? And whichever one makes the biggest noise here, in this case, the green, excitatory is going to fire the neurotransmitter. Okay, so you have these decision-making processes occur all the time in this. And that's just all that's showing. Nothing more than just showing how they're competing against each other. Not really worried about that. We can skip that. Okay, moving on. That's just nothing to that. It's just showing that there's competition between those. Summation leads to whether it fires or not. But when it fires, it's all or none, right? There's no partial action potential. Okay, now, these neurotransmitters, though, is very interesting to me. Once they release, they have to be reabsorbed back into the axon terminal or destroyed. And we saw the enzyme acetylcholinesterase, remember, broke down acetylcholine to help stop muscle contraction. So here is acetylcholine looking like Pac-Man eating the neurotransmitter to stop the continued firing of that action potential. So we got to have a way of getting rid of that. That one, that could be a good video. Let's see.
Synaptic transmission.
I'm just going to kind of paraphrase it here. Look, there they are. They're firing, and now here comes the neurotransmitter is either reabsorbed, or in this case, it's going to show it diffusing out of the way, or it can be broken down by the enzyme here is acetylcholinesterase breaking down acetylcholine, or it can be carried back in, put back into, reuptake. And so probably the most common psychiatric drug right now is serotonin reuptake inhibitors. Serotonin is released in this gap in your brain, and it's immediately retaken back up. And these drugs people take stop the reuptake so that serotonin levels stay high in these synapses, and that helps them deal with things much better. So that's a great example of a very famous drug that's probably the most common drug being given to people right now for depression or any type of mental state. Pretty fascinating. All right, so let's look at some of these neurotransmitters. That's more important to me. Nothing much there. Here's talking about how some of the black widow toxins causes massive release of neurotransmitter, overstimulate the postsynaptic neurons. Look at that. A bark scorpion, also look at that, prevents sodium channels from closing. So a lot of these, right, are altering that neurotransmitter, altering that synapses. Here's a little summary showing how all of that can happen at one time. And who's going to win here? The green stimulatory and the excitatory overcome the inhibitory, and you get a threshold reached here at the trigger zone. So really, when a neuron is deciding whether to fire or not, it's a summation of all these fire, don't fire events. And I like the ripple, you know, like the rock in a pond, the bigger the wave. When you get the big enough wave down here to the trigger zone, then you trigger an action potential. Okay, now let's look at these different groups. There's over 100 of these, and there's a table here that shows a few of them. We'll just hit them real quick. Some of them are another. Don't let the term scare you. Some of them bind to a receptor and are ionotropic, means they open up ion channels. Others are metatropic, meaning they're metabolized, and then that's how you stop the neurotransmitter. Okay, so it's an enzyme it binds to. Is what that means. Others bind to what's called, and this is pretty wild one here, because I wouldn't show it right here. This is one really important, and they just decided to drop a bomb on you here. But this is how hormones work. Hormones bind to a receptor, and they're metabotropic, and they bind to this receptor that triggers a G protein to produce a chemical inside the cell that would not appear without that hormone binding. And so in this metaphoric statement here, the hormone, which by the way, hormones and neurotransmitters are very similar, right? Matter of fact, norepinephrine is both a neurotransmitter and a hormone. Neurotransmitters can be hormones. Hormones are going to do the same thing. They bind to receptors on the surface of the cell and trigger a second messenger to be produced. The first messenger is the hormone itself, or the neurotransmitter. In this case, in like 1995, 96, we discovered that the most common of the 20 hormones, probably 10 or 12 of them produce cyclic AMP in the cell. So cyclic AMP is a chemical made from ATP that is the second messenger that triggers the cell event. For example, LH on day 13 from the pituitary gland goes down to the female ovary, binds, produces cyclic AMP, and you ovulate the next day. That's what triggers ovulation. Just an example. So that's when you hear about second messengers, that's just referring to the chemical made in the cell by the hormone or neurotransmitter binding to a surface receptor. Then we have a picture of that. Here we go. So here's the neurotransmitter binding, and there is a second messenger being produced in the cell. So they can bind to an ion channel and open it up. They can bind to a receptor that triggers an enzyme to activate in the cell. In this case, a second messenger that binds to an ion channel to make it open from the inside. Pretty complicated. Majors biology has a whole chapter on how all these can happen, but that just shows you. But this is how hormones work too. Okay, here are the major ones. We get to this table. Let's just look at this real quick. And like I said, I don't think I'm going to put a lot of these on there because they're all they run together, but they didn't do a good job. I would like a little bit better one here. But for example, acetylcholine, we already know that one is the one that triggers what? Neuromuscular junction in all skeletal muscle. It also is major league player in brain and spinal cord and CNS. It's generally excitatory. Okay, and then these are different little amines. The catecholamines, norepinephrine, epinephrine, dopamine, excitatory, right? And they affect the brain and spinal cord. Heroin mimics dopamine. So one is heroin work, and the opiates, they are very similar to the endorphins, to the enkephalins and the dopamine. Actually, down here are the opiate ones, right? And the enkephalins and the endorphins are called the opiates because they are opium. Heroin is chemically similar to it, and they cause you to have like an 8-hour or 5-6 hour coma, basically. Okay, here's a weird one. Neuropeptide Y is excitatory. That's a weird one. Here's substance P is the pain neurotransmitter, so we called it substance P. Others, glycine, GABA, glutamate, histamine, serotonin, they have multiple functions, but they come in different classes. Little amines, little ring structures here. These are amino acid ones, and then these are very small neuropeptide ones. But anyway, not going to go crazy. You can see how they're like over 100, but these are the main ones in the body. And I thought this is really cool because our opioid problem we have in America, the heroin, I mean, and all that mimics the endorphins. The best example I can give you of endorphins is, and I have done it. I haven't done it in a while because I've got fat again. But if you ever start really get into running, I know some of y'all run. You ever experienced a runner's high? And for me, Mr. Toll, I'm with you, man. When I can go to the gym for the first 15 minutes on elliptical, I feel every bone in my body aching. I am dying. I'm not going to make it. And for me, at about the 15-minute mark, I hear Rocky kick in. Dun 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 dun. Then I don't feel anything, and I just keep going. When I got in good shape one time, I was going to do a 30-minute ride one day on a stationary bike at the house. They had arm movement, and Alabama was playing Ole Miss, and I'm an Ole Miss fan. I said, well, I'm just going to ride the first quarter, or I'll just keep riding until Ole Miss is still in the game. Well, it went into overtime. So I rode like 3.5 hours, rode like 60 miles. Okay, crazy. I felt good until I stopped, and the endorphins kicked off, and I was in a coma the next day. So endorphins is that runner's high, and it's addictive. How many of y'all see people running in the rain, in the sleet, in the snow? I have gone to bed at 2 in the morning, got up and rode 30 minutes because I couldn't sleep because I hadn't got my fix that day. But it's a legal fix. It's not heroin, it's endorphins. And so your body craves it every day. And that's what you want to do in exercise, get to that point. And I know some of y'all have felt that. That's pretty fascinating. There's the enzyme breaking down acetylcholine. We'll see it used quite a bit. Norepinephrine, adrenaline, norepinephrine is the sympathetic nervous system neurotransmitter that causes the heart to go up. Okay? So kind of interestingly, check this out. Remember I did the sympathetic parasympathetic nervous system? Real quick, this is a point, big one. At the synapses on all your internal organs, heart and lungs and everything, the sympathetic neurotransmitter released is norepinephrine, which is the same thing as epinephrine, adrenaline. And that causes heart rate to go up, breathing rate to go up, your eyes to dilate, but it slows down heart rate, it slows down digestion, liver function, making urine, stops urine production, stops packing poo-poo in the colon, stops digestion completely. Okay? Now go with me. So that is right here, norepinephrine is the neurotransmitter released on all the sympathetic nerves, the fight or flight nerves. The parasympathetic nerve neurotransmitter is acetylcholine. And it would then make the heart rate go down and breathing rate go down, but that would fire up digestion and all the homeostasis, make some urine. Let's pass the food on down, right? The digestive tract. So these two competing, parasympathetic speeds up housekeeping, slows down fight or flight, sympathetic fires up fight or flight, slows down housekeeping. So when we had our second baby 20 years ago, we had to do a C-section because we had a C-section the first time. So we go to the Oxford Hospital to have our baby, and we pick her birthday. It's the only other birthday other than mine that I remember is 2/22/2000, when she was born. And we go, and they give my wife a little sedation, and they said, we'll start the surgery in like 30 minutes. Let's let the drugs knock your wife out. Y'all can wait in this little pre-surgery room. Well, being an A&P teacher, I looked over there, and they had a crash cart. So what do y'all think I did? I didn't steal nothing, But you know, I had to open the drawers and look in there. On the top drawer, they had 2 plastic trays full of little 1 milliliter syringes with 2 drugs. I'm going to let you guess what 2 drugs would be in a baby crash cart in case the baby is born and mama is on crack and that baby's heart rate is too high. There was what? Acetylcholine in there to slow the heart rate down. They could inject that in the baby. And right next to it was what? Epinephrine, adrenaline, in case the baby was stillborn and we wanted to force it the heart to beat. So those are the 2 drugs right there in that delivery room. One of them is going to be what? Norepinephrine to trigger a heartbeat and acetylcholine to slow it down. Now, I don't want to endorse any movies because I'll get in trouble, but I did see this movie, and if you've never heard a 4-letter word, do not watch this movie. Do not watch this movie. But how many have seen Pulp Fiction? Okay, those are the cool people in the room. Okay, when they take that needle and stab it into her heart, that is adrenaline they shot in. Now, I actually called a doctor after that movie, and you never stick a needle into the chest. You just break the needle probably, or you now have a hole in your heart. But what you do is you inject it into the veins and just do 2 chest compression, and it gets sucked right in. So you just do chest compression until it gets there. But that is adrenaline found. My inhaler is epinephrine, right? This one right here. And what does that do? Causes my bronchioli to what? Open up so I don't have wheezing and I can breathe. The EpiPen is to stop what? Anaphylactic shock, which is overreacting, and that triggers the release of the smooth muscle and allows you to breathe. So very cool. EpiPens, y'all have all heard of that. All that comes down to these 2 very important ones there. We're going to come back to that in chapter 14 and look at that. Others here, serotonin, look at this. Mood regulation, emotions, attention, feeding behavior. This is the target for the ADA drugs and all those for attention deficit disorder, all these, mainly serotonin. Parkinson's disease, very bad disease. Parkinson's is a dopamine inefficiency, okay? And we know that we can make synthetic dopamine. We brought people out of comas before, but then their brain quits responding to the fake dopamine. A movie called The Awakening, one of the few movies that, what's his name, that died a couple years, the comedian, right? Oh my gosh. Anyway, he plays a serious role as a doctor who developed dopamine. Pretty sad movie there. Awakening. They brought these people out of the comas that they were in due to Parkinson's disease, and they thought they cured it because they were not getting enough dopamine. But then the dopamine wore out the receptors, and so they only had 3 or 4 months, and they went back into that coma. Here's the substance, the pain neurotransmitter. We already talked about pain relievers. And look at this. Neuropeptide Y is a new one discovered that involves feeding behaviors. It may be why Robin. Okay, how many of us do this? And I'm taking part of the blame. I overeat. But I can eat a whole 5, 6 pieces of pizza. About 30 minutes after I do that, I feel hungry. I feel full. My feeling full is delayed. I know people that can look at a piece of pie and they feel full. They're making this substance, this neuropeptide Y, faster than others, possibly, which would be a nice problem to have. Psychiatric disorders affect the neurotransmitters in the synapses, right? And so all of our pharmaceutical drugs either help remove them or leave a neurotransmitter in that gap longer. Schizophrenia, yeah, very tough one here. Repeated psychotic episodes, period during which the patient is unable to test beliefs and perception and reality. Excessive release of dopamine has been associated with this, and we can give them drugs that block postsynaptic dopamine receptors. I had a friend of mine that had this, and I may have told y'all about this already. She was a brilliant teacher, but she would have the same psychotic episode like 4 times while working here. So she would have a nervous breakdown, drive and wreck her car, and thank the EMTs or the 12 disciples, and she would get out of the car and say, "Take me to Jesus." And she'd have to go to Lakeside for like a month or 2 to a mental institution to get back on her drugs. And her drugs made her gain weight, so she would quit taking them, thinking she had cured herself. Very, very traumatic, very tragic thing. She was way smart, very brilliant, way smarter than me. And most people, our depression disorder drugs are selective serotonin reuptake inhibitors, like I was talking about. And that serotonin seems to be a major one in setting the mood. Okay, but schizophrenia can be very, very scary. Another one that's really wild is bipolar disorder, anxiety, right? A lot of people take is fear. exaggerated, inappropriate fear. I had some friends that this COVID-19, they've had to go to a psychiatrist because they were so anxiety, scared to come out. I mean, scared to even go get the mail. I mean, very, very, very sad. And that seems to be GABA related. And then bipolar disorder, look at this, characterized by episodes of abnormal elevation, mood, followed by depression. Treatment usually decreases action potential generation, generally blocking sodium channels. I have a really good friend of mine that like 25 years ago, they've been married, this happened 25, 30 years ago, and the wife was the most fun person I've ever been around. She's the life of the party. And then when she's on the low, then there is nothing like her low. So she had the extreme highs and lows. And when she was high, she would get paranoid. I was riding with her in Memphis one day. She was driving, and she said, "Do you see the van behind us?" And I tried to look back. She said, "Don't look." And then she did 100 driving through Memphis, going right, left, up and off 240, just going everywhere. Ain't no van behind us, y'all. She's seeing it. And we finally hit a stop sign, and she finally stopped at one. And I pulled the emergency brake and took the keys out of the car and took her to a doctor. That's what I did. I took her to her husband and said, "We got to get her some help." Okay. And so she started taking drugs for her bipolar. And so she doesn't have the extreme highs and lows anymore. And it saved her life, I think. So not making fun of anybody with a mental thing. This is serious stuff. And they're saying now that 60% of America is taking a drug for a mental disorder. So that puts those people in the majority in America. Now, I think some of that's been overprescribed. That's another story. But these are really bad ones here. A lot of anxiety right now with COVID-19. Okay, the last part of this chapter I don't really care about, so we're just going to do it real quick. I'm not going to put a lot of this on the test. This is just neural pooling. We're talking about how the neurons work together. I'm not going to ask any of this. But you can see how one neuron could fire a bunch of muscles, right, by amplifying, and then one receptor could go to a lot of parts of the brain. Okay, so that's just mumbo jumbo, convert. I'm not going to ask any of that. Here's another set with epileptic seizures. I've had people have seizures in my class. This is a recurring episode of abnormal disorganized electrical brain activity. So it is brain neurons firing, which we can't control. And so they overwhelm the circuit and you get convulsions or multiple. And they say now it's not to try to hold these people down, let them have their seizure, but just make sure they don't hurt themselves. You might, put something in their mouth or something, but you really just need to let them have their seizure. Okay, and it talks about partial and generalized ones. Therapy right there, and there are drugs that you can take. Does anybody have migraine? Migraine is a blood flow problem to the brain. So migraines are too much blood flow cut off to the brain. Okay, hang on, let me look here. Probably could have spent a little bit more time, but I'm not going to put a lot of those neurotransmitters. I didn't really, the book's not very clear on them, but just maybe the big ones there we may talk about. Okay, I'm going to pull the next one up real quick, just see where we're at. I think the next one is the brain. Actually, I tell you what I'm going to do. I'm going to jump over and show y'all the rest of that sympathetic, parasympathetic, because I got a second here and I'm going to use it on that. Then we'll come into 12 hard tomorrow. But to me, this is really cool. Look at this. And I almost always do this in my lecture. When I show that picture of the breakdown of the nervous system, I just jumped to 14. And look at this. Okay, so check this out. Hold on. I'll get you to it. There's a cool picture here showing this. This makes sense. Now, there's a lot of mumbo jumbo in here, but look, right here it is right here. So here are the sympathetic nerves that come off the spinal cord, right? Now I'm talking about the autonomic nervous system here, guys. Okay, everybody with me? Autonomic nervous system. Okay, and look, eyes dilate, heart rate goes up, breathing rate goes up, you sweat, you cut off digestion, and you cut off genital activity and no kidney function. So sympathetic nerves are going to wake you. Eyes dilate, dilate bronchiola. That's what epinephrine. This is epinephrine's a neurotransmitter does this. Increase heartbeat, and then stop, relaxes digestion, decreases all of that because it's fight or flight. Now watch this next one. Now here is the parasympathetic. Remember, it's the vagus nerve. Look at this, and some of the sacral nerves. Here is. So here's the parasympathetic. Constrict eye pupils, slows heart rate down, closes breathing, increases digestion and urine function and bladder activity. Okay, let's think about that. Is this not the coolest thing ever? So you got these two competing nerves, right? The vagus nerve is going to be increased housekeeping and slow down heart rate, breathing rate. Then you've got the sympathetic nerves that come off the spinal cord, and they go out and they do fight or flight, and they fire up the organs that we need to stay alive for a few minutes. Does that help a little bit? Seeing these are the two divisions of the what? Autonomic nervous system, right? And that's the nerves coming out of the spinal cord, coming out to the body. Okay, now how many of y'all have ever, let me give some examples of this. Okay, I'll go ahead and do my favorite one. Okay, here's the assignment for y'all. Okay, y'all ready? Next time, now look, be careful of this. Now I'm not telling you, don't go any farther than I say, but have you ever watched them play poker? You ever been to Vegas and seen people play poker, watch them play poker on ESPN? They were at World Championship Poker. Why does everybody have glasses on? Shades. Because you cannot control the eye. The eye is autonomic nervous system, right? So check this out. So if we're playing high stakes poker and you get 4 aces or royal flush on the draw, what's your eye going to do? Your pupils dilate and you can't control it. They're going to go bam because you're excited. And then everybody throws their cards in. Okay, so here we go, Megan. You ready? This is some homework. So the next time you girls decide to ask a guy out and you see this guy and he's probably shy, just ask him out. Take him out on a date, okay? Take him to the movie, take him out to eat, buy him supper. And then when you take him back home and you do that, and you've been on this before, probably that very awkward walk back to the door, right, with that guy. But now you're in control. Walk him to the door, and when he's expecting to give you that arbitrary goodnight kiss, maybe just a peek on the cheek, you know, just a real nice kiss on the cheek, I want you to grab him passionately and kiss him in just a little bit of tongue, and then look at the eye immediately. If the eye dilated, the eagle has landed, he likes you. If the eye closes down, just get in the car, delete them from your phone. They're never going to go out with you again. Help me out here, guys. Help me out here, William. Talbert, where I needed Julian today. He ain't here. But how many of y'all been on that date before and the girl does not want to go out with you again? Then you call her the next 3 weeks and like her dog died, her uncle's brother, sister died, and then granddaddy distant. They just won't tell you, I don't want to go out again, right? I've had people have a lot of success. The eyes don't lie, right? If you want to know if somebody really enjoyed it, the eye has to dilate when you get excited. And same thing playing poker. That's why people wear shades playing poker. Is that not a cool one? That's a pretty cool example to me of that, right? You can't control the eye dilating. Okay, pretty wild. Okay, when football coaches do what at halftime? They tell these emotional stories to get you to fire your what? Sympathetic nervous system, right? To get the adrenaline being produced. So that, and I have seen the worst team win the second half because the coach fired them up and got their adrenaline flowing, right? When I was in the 10th grade, our team, we were like the year before I played my 9th grade year, they were undefeated. In my 10th grade year, we get down 21-0 at halftime. I mean, literally my 10th grade year, and I'm holding the chalkboard. The coach takes us into the public boys' bathroom and goes in there and kicks the water cooler over, rips his shirt off. Then he starts crying, and he told us this story about how he was on the kickoff team in high school. And for anybody who played football, the guy on the end has containment, and he was on the end, and they go down the kickoff, and the guy gets around him, scores a touchdown. They lost. He was a loser. He was the reason they lost. And then he had to go to see his mother in the hospital. He was dying, and she asked how the game went. And he said, "I lost the game," and he had to live with that the rest of his life. And then he tells us, y'all are down 21 points. Y'all played like crap. Are you going to have to live with this the rest of your life? We came out the second half and came back and won that game and pillaged that team because we were all crying. The coaches were crying. Everybody, all the coaching staff was crying. I found out 10 years later his mama was in the damn stand. She ain't never been sick and died. Whole thing was a scam. But he got us fired up. We won the game. Okay? Almost trashed that darn locker room. It was on the road. It went at home. We came out of there like some kind of crazy team. So sometimes emotions can be good, right? Sometimes they can be bad. But to me, this is so fascinating how God, and this is, y'all know, this is why the dog attacks you when you go to somebody's house, right? Because they trigger the fight or flight. And they do tell post workers to not run because dogs have a fight or flight instincts. When they see something running, they got to trace the enemy and track them down. That's when the dog chases you. Try it sometime. Big old dog comes at you, just go, stop. That works about maybe half the time. Okay, but anyway, if you're slow, you got no other choice, right? They always say, you know, who gets eaten by the bear, right? The one who we trip. The person we trip for food, the rest of us get away, right? Okay, but anyway, pretty interesting to me. Another one that always comes up, I will just say down here, it actually talks about it in the chapter, for the reproductive system to work, which, by the way, is autonomic, right? You don't have conscious control. Parasympathetic primes the boy, and then the orgasm for boy and female, girl and boy both, is the sympathetic nerve firing. So you got to have both of these firing. Okay, but here's the point I want to end with. Okay, how many of y'all have somebody that's paralyzed? Know anybody paralyzed? Okay, I actually knew Chucky Mullins. I didn't know him well, but I met him. He didn't know my name, but we saw him because that happened when I was at Ole Miss when he was paralyzed. And I always wondered how paraplegics are alive. Okay, here's one of the metaphors. If you break your spinal cord, you lose what? All your sensation, but you also lose your what? Sympathetic nerves, the somatic nerves, the conscious control. But because that vagus nerve is outside, it's a cranial nerve, okay? And here it is right here. Let me go back to it. Because this vagus nerve is a cranial nerve, then it is not broken in the spinal cord. So you can still, heart control, breathing rate, and digestion and urinary is still working. So it's not in the spinal cord. It runs outside and it's loosey-goosey and it don't break in a car wreck. Now, obviously, you decapitate somebody, they dead. The whole game's over. But where you damage that spinal cord, you still feel everything from there up. But the vagus nerve is why paraplegics are usually can live for a long time. But they won't know if they have an infection or whatever. You know, like Christopher Reeves, who plays Spider-Man, remember? He's played Superman in the very first Superman movie. Remember, he was paralyzed at like C3 or C4. So he had to breathe. He couldn't even breathe on his own until many years of therapy. Because the respiratory one is real high, like right here, look, it's right there. But the somatic nerves on that, you don't want to, the farther up toward the head, the more dangerous it is for the spinal injury. So a lot of cool things there. But I think the vagus nerve staying intact is how paraplegics stay alive, which is kind of interesting. You always wonder, if you break your spinal cord up here somewhere, then how can you still be alive? That vagus nerve, as long as it's intact, you can stay alive with just one throttle. You don't have to have sympathetic. You just got that one throttle. All right, questions. Are we going back? But I thought that was kind of cool to throw that out there and show you that completion of. So one more time: central nervous, peripheral nervous system, right? Central nervous, brain, spinal cord. Peripheral are all the nerves coming off the spinal cord. Somatic are those that you conscious control. The autonomic nervous system is divided into the parasympathetic we're seeing here and the sympathetic right here. And they, in combination, control the entire body.
Mr. Robison, your
Yes.
screen's not shared.
Huh?
Your
It's not
screen
sharing?
is
Okay, sorry. Okay, I'm sorry. Y'all got to tell me that because I was showing it to you. So there, look, there it is. You see it now? There's the sympathetic nerves, right? Look, coming off, look. And there it is, causing dilation of the pupil when you get excited. Increased heart rate, increased breathing rate, stops digestion. Sorry, this is a really cool picture. And let me find the other one here. Hang on. Let me find my page turner. Hang on. Why is it wanting to be like this today? Here we go. I just got to click it. Look at this. Sorry about that. Hang on one second. And here's the other one. Look, there's the, I went too far. There's the parasympathetic. There's that vagus nerve. Look. Sorry about that. Isn't that cool? Hey, you got something to sign? Hey, here you go. All right, guys, we're going to call it there today. Anybody else? I just wanted to show you those two because that's how I usually jump over to this in the chapter 11. All right, I'm going to call it a day. I'll hang on a minute. Let me sign something here. I got my guys are delivering some stuff here. Hang on a minute. More stuff. All right. Hang on. I'll answer some questions. Just lay it on the table. I'll put it in. I just let it in there in that kitchen table. I'll lay it over there. Y'all guys good today?
Yes, sir. How about you?
I'm running wild. Yeah, we're good. All right. Questions, anybody? Sorry about that, but isn't that kind of cool? Those are your nerves right there. It's that chapter 14 is relatively short. That's about all I want you to know. And we got a short answer question out of 14 that I will go over probably Wednesday. All right, question, anybody?
I have a question regarding the mastering homework, the 11 through 14.
Yep.
You have that due Wednesday morning. Is there
Yeah.
any particular reason why it's due Wednesday morning, not Thursday?
Because I don't want y'all doing the homework on Wednesday. I want you studying for your final. Yes. I want it done Wednesday, so you won't be doing it on Wednesday night, and you're gonna fail the final because it counts 12% of your grade, and all that homework don't count, but 12% all we've done. So I just wanted y'all to get that done before the final, so you'll have a day to stay for your final. I did, William. I did.
I was just making sure.
No,
'Cause
I appreciate that. No, that's a very fair question. Now, that's exactly what I was doing. So that was set up for, that was intentional, because I wanted y'all
my
not to.
thinking was studying for the lab final Tuesday night, but that makes sense. Probably studying the mastering homework will help with the lab.
Yeah, I think so. I do. And like I said, I know we got quite a bit of that, and we'll talk about that in lab tomorrow about the lab stuff. I know a lot of that's great that y'all doing working on that. Hopefully this weekend. But yeah, I did set it all. I just didn't want y'all, because what happens is some of y'all be doing it Thursday morning instead of studying for your final. So I'm just trying to get all of that done the day before.
Yes, sir.
And I know it's a lot, guys, and I'm sorry. This is the nature of summer school. It is so freaking fast. But anyway, we got a lot covered today, and I hope y'all felt good about it, because half of the day was what? Repeating Acts potential, right? And so those of y'all that got all their points on that, I'm not going to expect you to do any more than that. I'm not going to make you go into all the different states of that sodium channel. Does everybody feel okay about that one now, about the Acts potential? And by the way, those videos are in the study area, in your lecture area on mastering, that big picture area, and you can watch every one of those again. So I think they're pretty darn good. I'll look over the test today so I can, but I know the Acts potential, I believe, is only, hey, hold on. Well, we got a minute. Let me take a look at it. See if I can find it. All right, I'm having fun finding it now. That's even better. All right, I gotta find the file. Oh, there it is. So remember, we're gonna have 50 multiple choice O and 50 new, and I've got short answer questions, not many, because I'm gonna be able to grade it quick. Describe an Acts potential again, 4 points. Question about how the CNS can regenerate while the PNS can't. Remember, excuse me, the PNS, peripheral nervousness, can regenerate because of that neurolimia tube, and the CNS cannot. Then I've got a 4-point question on the 4 differences between sympathetic and parasympathetic that I will give Wednesday when we cover chapter 14. So that's about a 30-minute lecture on that. And so really we've got, and oh wait, you're gonna love this. Hold, everybody's finna cry. No terms on the final. So 100 multiple choice and 3 short answer questions. And that's it. So Merry Christmas. Look at Miss Gonzalez. She's excited. No terms. I'm gonna cry. So 3 short answer, and so 50 multiple choice off a nervous system, and then 50 over our different groups, of which I think 10% of that is 10 of those are nervous system ones, but they're really easy. Okay.
Mr. Robinson.
Yes.
So you're saying like 50 of them, like some of them are gonna be like old stuff. It's
Yeah, but they're big, broad stuff. I would not spend a lot of time on the old stuff, but it wouldn't hurt you to just flick back over it, like something like muscle contraction, calcium, stuff like the big things. I'm not going to have, there's no diagram, so I'm not going to ask the muscle name or something. Okay. But big, broad stuff. Okay. And I would think the mastering out of chapters 11, 12, 13, 14 are being very similar to the multiple choice questions, right? That I think a lot of y'all have been telling me a lot of that study area, the testing in there is very helpful. Okay. Oh, by the way, I just, FYI, I have 3 of these shirts, by the way. I just want y'all to know that I got them on sale at the bookstore. So somebody may want to wear the same shirt. I have 3 new ones of those I wear. So I don't have to wash them, but once a week I can wear the same shirt 3 days. Just FYI. Somebody's always like, dang, he wore that shirt Friday. Well, it's probably a different one Friday. Just joking with y'all. But true story, I have 3 of them. Anybody else? Good questions, William. I'm glad you said that, because that's exactly why. But I did know that lab final is Wednesday, right? And I do think it's going to be a lot easier on this online format. And we'll talk about that. I think Philip is doing the same thing I'm doing, right? So we're going to do that. So we're all going to be good there. So we're going to make it this week. We're going to survive.
For the lab final, is it going to be all like typing it in, or are we going to have some multiple choice?
I said it's going to be online. I think it's like maybe 10, 15%. You got to spell some of that. So a lot of it's going to be the word bank's going to be in there. It's going to be like, multiple choice. or labeling with pictures. Okay. And I think we have a practice online test. We'll turn it on probably tomorrow. Probably turn it on tomorrow. She'll have it. Well, obviously got to turn it on. I need to turn it on. I'll make sure it's on today. Maybe it should be on, but I forgot because that test is Wednesday. So I'll go in there. Look, if y'all, I know y'all are tired, but hey, I'm gonna be here till dinner, and then I'm gonna probably go home and eat and come back and work some tonight. So y'all can call me or text me, message me. I have my phone on. It's probably easier just do it through the message, just send me like the Canvas messages. It throws them to my email. The Canvas messaging, the Google Chrome thing, I miss it sometimes, but y'all can call it and it will ring and I'll try to answer. I had an online student text me last night at 12:30. I was not happy. I was not nice because he couldn't get his computer to work and wanted me to turn on the test for him. And I'm not going to. It was due midnight, right? Y'all know the drill. All right. Anybody else? I'm going to call it. I'm going to stop recording anyway, and I'll hang on here if you have a question. So I'll hang here a minute. Let me stop the recording.